The ground beneath you is hollow, riddled with cavities, unpredictable limestone voids that no map can fully chart. And someone decided to build one of the tallest structures in human history directly on top of it. Welcome back to the channel. Today we are looking at one of the most audacious engineering achievements ever attempted, a tower so tall, so heavy, and planted on ground so treacherous that its very existence feels like a defiance of physics. This is Merdeka 118, the world's second tallest building, and the story of how it was built is a story about geology, gravity, national pride, and thousands of people who refused to accept the word impossible. This is not just a skyscraper. It is a 678.9-meter column of engineered ambition rising from the heart of Kuala Lumpur, a city built on soft river plains, underlaid by some of the most geologically unpredictable rock on Earth. It is a building that had to solve problems no textbook had prepared anyone for. Problems that existed not at 400 meters in the sky, but 100 meters underground. In the dark, in the cavities, in the rock that kept changing its mind about what it was. Imagine you are the lead structural engineer handed this brief. You must build a tower with 118 floors. It must reach 678.9 meters. It must carry its own weight, survive tropical storms, withstand seismic tremors, and stand for centuries. And the ground is limestone karst, a geological formation, famous for dissolving, for collapsing, for hiding chambers and sinkholes and voids that can appear without warning. There is no baseline. There's no predictable bedrock. Every meter you drill might be solid. Every meter might be empty. And they decided to build the second tallest building on Earth right here. Before we continue, make sure you subscribe to the channel. Every week, we go deep inside the projects that changed what human beings believe is possible. And stay with us until the end. Because what the engineers found when they finally drilled down into the earth beneath this site is something that would have stopped most projects cold. At first, there was only a patch of urban land. No tower, no foundation, no core, just the city around it, the humid Galar air, and below the surface, that restless, unreliable limestone. The site sits in the Imbi area of central Kala. And it had history, the history of Malaysian independence woven into its name. Merdeka means independence in Malay. This tower was not a commercial vanity project. It was a national statement. Permodalan Nasional Berhad, Malaysia's sovereign national investment fund, was the developer, and they needed this building to mean something, to stand for something, to be something that could not be ignored, that raised the stakes beyond engineering. Failure was not an option. Not here, not for this. So the problem begins underground. If you simply drill straight down and hope for solid rock, you will find voids. Cavities the size of rooms, chambers the size of warehouses. Karst limestone is formed over millions of years by slightly acidic groundwater dissolving the rock from within. Water seeps through cracks. It reacts with the calcium carbonate in the rock. Millimeter by millimeter, year by year, century by century, the acid eats the stone from the inside. What you get is not a predictable underground profile. What you get is Swiss cheese, except the holes are invisible, uneven, and can be anywhere. And the particular karst geology beneath Kala is among the most variable on Earth. It is not simply that the bedrock is deep, it is that the bedrock can be at 10 meters in one spot and at 60 meters 3 meters away. It dips, it rises, it disappears. And 20 molar, there are pinnacles of hard rock jutting upward like teeth, and valleys of soft material between them. It is the opposite of what a structural engineer wants. The result is a geology that looks solid from the surface, but may be riddled with hidden hollow spaces beneath. These are not small gaps, they are structural nightmares. A pile driven into a void transfers no load. It holds nothing, and a building of 678.9 meters, carrying the incomprehensible weight of millions of tons of concrete and steel, needs its foundations to hold everything. If you use normal pile depths, the voids defeat you. If you drill deeper and hit another cavity, you are no further forward. If you try to map the geology with conventional methods, you get a picture that changes every few meters. There is no reliable pattern. There is no shortcut, so the solution was not to find solid ground at a convenient depth. It was to go until you hit bedrock, regardless of how deep that took you, and then build anchors so large and so deep that the building's weight would be spread across dozens of massive load paths, any one of which could fail and the system would still hold. The foundation investigation alone was a project inside a project. Before any construction could begin, a full geotechnical survey of extraordinary complexity had to be completed. The engineering team, led by structural engineers Thornton Tomasetti, working alongside specialist geotechnical consultants, began by drilling exploratory boreholes across the entire footprint of the site. Not a few, not a dozen. Hundreds of individual drill points, each one providing a core sample, a thin cylinder of earth extracted from deep underground, like a biopsy of the ground. Each core told a story. This layer is soft clay. This layer is decomposed rock. This layer is granite. This layer is a void. This layer is solid limestone. And the story changed from borehole to borehole in ways that made the picture more complicated with every new data point. They probed, they tested, they mapped every anomaly. They used geophysical surveys, seismic refraction, resistivity imaging, ground-penetrating methods to detect cavities and profile the rock before the piles went in. Every single meter of ground was interrogated before a single structural pile was placed. They needed a portrait of the invisible, a map of what could not be seen because the entire structure above would depend on that map being correct. This investigation took time. Months of drilling, months of testing, months of analysis before the first concrete was mixed. And that time was not wasted. It was the most valuable investment the entire project would make. Because a foundation designed without that knowledge is not a foundation. It is a gamble. And nobody gambles with a 678.9 meter tower. Then came the piles, board cast in place concrete piles of enormous diameter, driven deep into the earth, in some cases more than 100 meters below ground level. These were not hammered down like nails. They were drilled a rotating cutter boring through rock, through soil, through decomposed granite, through bands of clay, through whatever lay between the surface and the bedrock the engineers needed. The drilling rigs that did this work are machines of extraordinary power. They sit at the surface, anchored to the ground, and extend a rotating drill string downward under enormous torque. The cutters chew through rock at a rate measured in centimeters per HR in the hardest material. The cuttings are flushed to the surface by drilling fluid, a slurry that also supports the walls of the borehole to prevent collapse. While the pile is formed, once a borehole was completed, the process of building the pile began. Steel reinforcement cages assembled at the surface from individual bars of high-yield steel, bound together with links and spacers, sometimes meters in diameter and tens of meters long, were lifted by crane and lowered into the borehole section by section, connected end-to-end until the full cage reached from the bottom of the hole to the surface. Then the tremie pipe was lowered, a tube that carries concrete down to the very bottom of the hole, displacing the drilling fluid upward from below. Concrete poured, fluid pumped out, pile formed, and each pile was tested under load before the next phase of construction could begin. This was not engineering by assumption. This was engineering by proof. Every pile had to earn its place. Every pile had to demonstrate it could carry what the tower would demand of it. The tests involved loading each pile with forces that simulated a portion of the building as eventual weight, watching for any settlement, any movement, any sign of failure. Without those tests, there could be no confidence. With them, there was certainty. Every pile mattered. Every anchor point mattered. The foundation system that emerged from this process was a deep basement, 5 levels underground, a subterranean world of reinforced concrete walls, slabs, columns, and tie beams that would eventually carry everything above. The excavation for this basement was itself a major undertaking, a deep cut into that unpredictable limestone with ground anchors and retaining walls holding back the surrounding earth, while workers carved out the volume below. Fike of those, Phi for pride, Y Geeston, the Friedchen, T-shirt, Vigen, then Fiberden, Yn, 5 levels layers of structure going downward before a single floor went upward. Before the tower could rise, it had to burrow. Then came the core. The central concrete core of Merdeka 118 is the spine of the building. It rises from the foundation level to the very top, a hollow tube of high-strength reinforced concrete that houses the elevators, the fire stairs, the mechanical shafts, the communications infrastructure, and the structural heart of the entire tower. The concrete in this core is not ordinary concrete. It is high-performance mix, designed to carry enormous compressive loads, resist cracking, maintain strength over decades. The core walls are thick at the base, meters of solid reinforced concrete absorbing forces that would destroy lesser material. To build the core, the construction teams used a system called jump, forming a process where formwork climbs the structure as concrete is poured, allowing the core to grow floor by floor in a continuous, relentless upward rhythm. A climbing formwork rig perches at the top of the already poured, new reinforcement is placed, fresh concrete is poured, and then again, par 118 times. This was not fast, this was methodical. Each pour had to cure to a minimum strength before the next one could be placed on top. The concrete mix was designed with precise water, cement ratios, admixtures to control heat of hydration, and carefully graded aggregates to achieve the required density and strength. In the tropical heat of Gollifer, where temperatures regularly exceed 30 degrees Celsius and humidity is relentless, controlling the temperature of fresh concrete became a science of its own. When cement hydrates, it generates heat. In a thick concrete wall in a tropical climate, that heat builds up. Too much heat causes the concrete to crack as it cools and contracts. So the concrete mix for the core walls was designed with supplementary cementitious materials. Ground granulated blast, furnace slag, fly ash that slow the hydration reaction and reduce the heat peak. In some, pores chilled water was used in the mix. In some, ice replaced part of the water. The goal was always the same: control the heat, prevent cracking, achieve the design strength. In the lower floors, the core walls had to carry not just the weight of the floors above, but the accumulated construction loads. The cranes, the materials, the equipment, the workers, all perching on a structure that was still growing. Around the core, the building's megaframe began to take shape. Merdeka 118 uses a composite structural system, a combination of the reinforced concrete core, outrigger systems at multiple levels, and a perimeter megaframe of large steel and concrete composite columns. The outriggers are giant structural members, deep trusses or concrete walls that connect the core to the perimeter columns at key floor levels. This link is critical. Without it, the core alone would be too slender and too flexible. With outriggers, the perimeter columns take a share of the lateral load from wind and seismic forces, dramatically stiffening the structure. Imagine a flagpole, flexible, prone to swaying. Now attach cables from the pole to anchors in the ground. The pole stiffens, it resists the wind. That is the principle of an outrigger system, applied at the scale of one of the tallest buildings on Earth. The structural system that held all of this together include high-performance reinforced concrete core walls varying in thickness from the base to the top, outrigger trusses occupying full mechanical floor levels at multiple heights up the tower, steel and concrete composite mega, columns at the building perimeter carrying vertical load down to the foundations, belt trusses at the outrigger levels tying the perimeter frame into a continuous ring, high, yield revorbia, Monenberg spy fravors. Every bolt mattered, every weld mattered, every concrete pour mattered. The wind loads on a 678.9 meter tower are not abstract numbers in a calculation. They are a physical reality felt in the structure every single day. At the heights Merdeka 118 reaches, wind speeds are substantially higher than at ground level. The pressure of wind on a tall building acts like a hand pushing against the side, and the building must be designed to push back without moving, so much that the occupants feel sick, without stressing the connections beyond their limits, without allowing the structure to enter resonance, the dangerous condition where the building's natural swaying frequency matches the frequency of wind gusts, causing oscillations to amplify rather than dampen. The engineers at Thornton Tomasetti ran wind tunnel tests on a scale model of the tower, a careful physical simulation in which model airflow was used to measure the forces and pressure distributions on every face of the building at every angle of wind approach. Those test results fed directly into the structural calculations, ensuring that the real building's frame was sized for the real wind environment of central Kuala Lumpur. The facade of Merdeka 118 is not a flat glass wall. It is a faceted surface, thousands of glass panels arranged in a geometric pattern inspired by traditional Malaysian craft and the star motif embedded in the country's identity. The architectural design by Fender Katsoulides gave the building its distinctive shimmering quality, the way the tower changes appearance through the day, from a gleaming silver form in morning sun to a golden silhouette at dusk. This was not accidental. Each panel was engineered for its precise position, its precise angle, its precise fixing to the structural frame behind it. The curtain wall installation was a process of extraordinary precision. Individual panels, each one unique in its placement within the larger geometric pattern, were lifted by tower cranes guided into position and fixed to the building as steel structure. At these heights, wind is a constant variable. A panel that is manageable at ground level becomes a sail at 400 meters. The rigging, the installation sequence, the protection against wind loading during installation, all of this had to be designed as carefully as the panels themselves. And behind every panel is a world of engineered detail. The aluminium extrusions forming the panel frames, the structural silicone sealants bonding glass to frame, the pressure plates and cover caps holding the assembly together, the thermal brakes preventing cold bridging through the aluminium, the drainage channels guiding any water ingress to weep holes, the fire stops at every floor level preventing the cavity between the facade and the floor slab from acting as a chimney in the event of fire. Then came the upper floors, the sky lobby, the hotel. The observation level as the structure climbed past floor 80, past floor 90, past floor 100, the nature of the construction changed. The logistical challenge of getting materials, workers, equipment, and concrete to heights of 400, 500, 600 meters above the street is a discipline of its own. High-speed construction hoists temporary lifts running on the outside of the building. Structure capable of carrying workers and materials to the working level in minutes carried the teams who would never take the stairs if they could avoid it. Tower cranes themselves anchored to the building's core at multiple levels, jumping upward as the structure rose lifted steel sections, formwork panels, mechanical equipment, and prefabricated components from the ground far below. Each crane lift was a planned operation. The load, the rigging, the lifting height, the path of the load through the air, the zone below that had to be cleared. At the heights of Merdeka 118, a dropped object does not fall a floor. It falls hundreds of meters. Every lift was managed with absolute discipline. The concrete pump lines that fed the core climbed with the structure, capable of pushing concrete vertically for hundreds of meters against gravity, through pipes that snaked up the building as interior to the formwork above. The pump pressure required to push concrete to 600 meters is extraordinary. The pipelines carrying it must be rated for those pressures. The concrete mix must be designed to flow under that pressure without segregating, without the heavier aggregate settling to the bottom of the pipe while the cement paste rises. Every pour at upper levels was a carefully managed operation. The construction of the spire that crowns Merdeka 118 was one of the final structural acts. The spire is a structural steel assembly that lifts the building's total height to 678.9 meters, a number that places it definitively as the world's second tallest building, behind only the Burj Khalifa at 828 meters. The spire sections were fabricated off-site, transported to the building, and lifted by crane to be assembled at the summit. At those altitudes, weather windows for crane operations are narrow. Wind speed thresholds must be respected. A crane operator working at the top of Merdeka 118 is working in conditions that have no parallel in most of construction practice. The city below is a pattern of rooftops and roads. Clouds pass at eye level. The horizon is curved, and in this environment, tons of structural steel must be guided to millimeter precision and connected to what came before. The building was topped out in 2021. The moment the final spire element was placed, Merdeka 118 achieved its full height and announced itself to the world. But topping out is not opening. The years that followed were filled with the interior fitting the mechanical systems, including chillers, cooling towers, air handling units, ductwork, and pipework running through every floor. The electrical systems, including high-voltage switchgear, distribution boards, cable trays carrying hundreds of kilometers of cable through the building's risers. The plumbing and drainage systems serving thousands of fixtures across 118 floors. The fire protection systems, including sprinkler pipework, smoke detectors, voice alarm systems, and pressurization systems for the fire stairs. The elevator installations, multiple banks of high-speed lifts serving different zones of the building, their machine rooms, their guide rails, their counterweights, their cab interiors. The interior architecture of the hotel rooms, the retail spaces, the Sky Park floors, the ViewSat 118 observation deck, all of it rising inside the shell that the structural team had built. Without the board piles reaching bedrock, this tower settles and tilts. Without the mapped geology, the piles go into voids. Without the outrigger system, the core sways and the building fails to stand. Without the composite megaframe, the lateral loads from tropical storms destroy the perimeter. Without the tuned mass damper, the upper floors oscillate and the building becomes unlivable. Without the wind tunnel tests, the structure is undersized for the real forces it faces. Without the fire protection systems, the building cannot be occupied. Each system depends on the one before it. The pile needs the bedrock. The core needs the pile. The outrigger needs the core. The mega frame needs the outrigger. The damper needs the frame to constrain. Without it, disaster. With it, miracle. This was not a building. This was an ecosystem of engineered systems, each one designed to support and be supported by everything around it. Most visitors to ViewSat 118 step out onto the observation deck and see only Gulliver spreading below them, the Petronas Towers to the north, the city grid fading into haze at the horizon. They see the view. They do not see the 100-meter piles in the limestone below the basement. They do not see the hundreds of bored holes drilled to map a geology that could not be trusted. They do not see the climbing formwork that inched upward, level by level for years. They do not see the outrigger trusses buried inside the mechanical floors, great steel structures visible only as a slight widening of a service corridor. They do not see the damper near the summit, moving in gentle opposition to the building's breadth. They do not see the curtain wall fire stops at every floor, the drainage channels behind every glass panel, the intumescent paint on every steel beam. They do not see the thousands of workers who spent years in the heat, in the noise, in the dust, assembling a structure that now looks as though it always belonged here. They do not see the geologist who plotted every cavity in the limestone and knew that one missed void could mean catastrophe. They do not see the engineer who designed the pile load tests and waited, watching the gauges, watching for any sign of failure that never came. They do not see the crane operator at 600 meters, guiding a steel spire section into position, the wind against the cab, the city, an abstraction far below. They do not see the concrete technologist who ran mixed designs through a tropical summer to find the right formula for the core walls. They do not see the curtain wall installer who spent months at altitude fixing panel after panel to a building that had no precedent in Malaysian construction history. Buildings like Merdeka 118 are named after the idea of independence, but what they actually represent is something more complex than freedom. They represent the accumulation of human knowledge, geological, structural, material, logistical applied with absolute precision to a problem that nobody had solved in exactly this way before. They represent the quiet heroism of skilled labor of engineering teams, of workers who built something that will outlast every one of them by centuries. There is a name for what Malaysia did when it built Merdeka 118 on hollow limestone ground, in a tropical climate to a height of 678.9 meters, with a design that honors the geometry of traditional craft. The name is audacity. The name is competence. The name is, in the deepest sense, Merdeka. Independence from the limits of what anyone thought could be done. If you found this story as extraordinary as we do, subscribe to the channel, hit the bell, leave a comment below. We want to know, what building or engineering project should we cover next? The world is full of structures built where no structure should exist. And we are just getting started. Thank you for watching.